So audio should be now on the YouTube stream. Can you guys hear me okay? Yeah, okay. Samarth, your mic is kind of finicky. Also, there's an echo. If you guys want to like mute your microphones if you're not like asking questions, that'd be good. And it would cut down echoes. Okay, perfect. All right, let's get started. So I figured we might as well pick off where we... Yeah, that's perfect. Awesome. Thanks, Mark. Okay, so on the Friday right before we went to break... hey, Samarth, do you want to mute your mic just so it doesn't echo? Awesome, thanks. Okay, perfect. So on the Friday right before we left off, we did like a rapid fire introduction of derivatives of exponential functions, as well as derivatives of sine and cosine, and derivative of tan. Now, I know we did like a few examples for each of those. I figured let's put a more formal lesson in place for that. And then, yeah, so I try to pick examples that I don't remember us doing together. But if I accidentally repeat one, then so be it. So again, recall that we introduced e, and e was like a special number, right? Just like pi. So e is an irrational number, meaning it can't be expressed as a fraction. So it's similar to something like pi or the square root of 2 or something like that. So I put e down here. So there's e. And the reason why we care about e, or specifically the exponential function e to the x, is that when we take the derivative of e to the x, we just get that function back again. So it's kind of a really interesting derivative, because the derivative of the function is the function itself. So I was going to do a quick little warm-up just to, bring us all back in together here. So if we switch over to Desmos here. So in Desmos, I've plotted a graph of e to the x here. And so I figured we might as well pick a point and then calculate IROC around that point. So maybe we can calculate, let's calculate IROC of e to the x right around the point x equals 8. Okay, so calculate IROC of e to the x at x equals 8. Just as a quick example, right? So what we should see is that the slope of the function at x equals 8 should be the value of the function. Or sorry, I'm looking at the wrong thing here. X equals 2. I'm rusty. At x equals 2, the value of the slope at x equals 2 should be 8. It should be the same value as the y value of the function there. Okay, so we should expect to see something approximately around 8. All right, so let's see if we can do that. So let's calculate the IROC of e to the x at x equals 2. So for that, we can use our difference quotient, right? So the limit as h approaches 0 of f at 2 plus h minus f at 2. Yep. Yes. Yes. But you from first principles though. Like into our actual derivative formula? Yes. So what we'll do is we'll compare to this afterwards. Yeah. Okay, cool. Okay, so let's plug in here. Plus, this is just an excuse to review the difference quotient, right? Not that we'll be using it a lot from here, but kind of why not? All right, so let's calculate this thing. So e to the 2 plus h minus e to the 2 over h. Okay. Okay, so now this thing kind of becomes a little bit challenging to actually solve for. However, there are some tricks here. So if we do limit as h approaches 0 of, we have, I'm going to take this thing and I'm going to split it up. So we get e to the 2 times e to the h. That's one of our exponent rules, right? And I'm going to use that here. So I get e to the 2 times e to the h minus e to the 2 over h. And now what I recognize here is that both of these terms in the numerator have an e to the power of 2 in it. So what I can do is I can factor out an e to the power of 2. So I get limit as h approaches 0 of e to the power of 2 times, and then all the things that are left over here. So I get e to the power of h minus 1 over h. Okay. And now this limit is actually a little bit tricky to kind of evaluate, because what we end up noticing is that we get a value of, if we just tried to plug in 0 into here, what we would get is e to the power of 0, now that's 1, minus 1, so that whole thing is 0, over h, or over 0, and so we actually get something that's 0 over 0, which sort of doesn't work out, right? Whenever we get something like that, that's where we have to introduce a whole bunch of limit tricks to kind of fix this thing, right? Now, unfortunately, we don't really have any limit tricks for this particular like example of function, okay? But what we could do is we could choose a very small value for h, a very small value for h. So Samarth, right now you're going through advanced functions. This might be the kind of method you would do in advanced functions, right? You pick a really small value for h, and then plug it in and see what you get, right? So if we pick a small value, say like 0.001, and we plug it into that formula, so e 0.001, so h equals 0.001. What we'll find is that this entire thing, this entire quantity here, this bracket quantity, simplifies to 1, okay? Which means this entire limit, when we evaluate it at h equals 0, simplifies to e to the power of 2, and now e to the power of 2 is approximately 7.3890, blah, 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 okay? So now let's see if that actually worked out, right? So if we go back to our Desmos graph and we go to x equals 2, we find a value of 7.389, right? So we nailed it right on, okay? So this example just shows that the derivative of e to the x is just the y value of whatever x value we have for e to the x, okay? So this kind of, this difference quotient example just sort of proves the fact that the derivative of e to the x is e to the x, right? Now, from here on out, we're not going to really be using the difference quotient. We're just going to be using this special formula, okay? Okay, a bit of a warm-up, but any questions so far? Are we doing pretty okay? Okay. Alrighty, so I don't think we did these examples, we might have done 1 or 2 of them, but I tried to pick ones that I definitely didn't remember us doing. Okay, so let's give this a go. So, derivative of 3 times e to the x squared. So let's compute the derivative, df by dx. The derivative of 3e to the x squared. Okay. So now for this, what I have to recognize is the fact that I have, I'm going to have to use chain rule here. And the reason why I have to use chain rule is that I have an outer function, right? I have like an e to the something function. That's my outer function. But I also have an inner function, right? I also have this x squared inside. And so I'm going to have to use, I'm going to have to apply my chain rule here. So the 3 is just along for the ride, right? That's just out front. The derivative of my outer function, so the derivative of the e to the power function, stays the same, so e to the x squared. But because I'm dealing with chain rule, I have to remember to multiply by the derivative of the inside function. Okay? So the derivative of x squared gives me 2x. Right? And now I can do just some quick simplification. So I will get 6x times e to the x squared. All right? So just a quick warm-up. Again, I think we did a couple like that on the Friday right before. I don't think we did this one, though. So next example here, determine the equation of the tangent to y equals e to the x over x squared, where x is equal to 2. All right. So let's take a look at what this thing will look like in Desmos here. So we have e to the power of x over x squared. Oops. So we get something that looks like kind of like this, and we are interested in the tangent line where x is equal to 2. All right. Now, from an initial look here, it kind of seems like we're going to expect to get a horizontal tangent line. Okay. So let's actually plug this in, and we'll see what we get when we do that. All right. Okay. So back to notes here. Okay. So to determine the equation of the tangent line, I have to take the derivative, plug in the value to figure out what the slope is, and then I'll have to plug in the point to figure out what the y-intercept is. All right. So let's start with the derivative. So y prime equals. Now, if I look at this function, I have two pieces that I have to be concerned with, right? I have e to the x in my numerator, and I have x squared in my denominator. All right. And so I'm going to have to use quotient rule here. All right. So quotient rule, what I have to do is take the derivative of the numerator first. So derivative of the numerator, that's just e to the x. And I keep the denominator the same, so x squared. Okay. Now to that, I subtract, so I keep the numerator the same, and then I take the derivative of the denominator, and then the entire thing has to be put over the denominator squared, so x squared squared. Okay. Now we can do a little bit of simplification here, right? So I can do e to the x, because that's common in both pieces here, right? I have an e to the x here and an e to the x here, so I factor. And when I do that, I'm left with x squared minus 2x. Okay. This entire thing will be over x to the power of 4. All right. And I could even factor out a x, because I have an x squared and I have an x. So I can remove an x from the numerator as well. All right. X e to the x times x minus 2 over x to the 4. And from here, I could even do a little bit of canceling, because I have an x over an x to the 4. So when I do that, I get e to the x times x minus 2 over x cubed. Okay. So I have found my derivative. All right. Now I'm interested in the equation of the tangent line here. All right. So to find the equation of the tangent line, I actually need the slope of my function at this point. So what I'm going to do is I am now going to plug in x is equal to 2 into my derivative to figure out what my slope will be. Okay. So y prime when x is equal to 2 is equal to e squared times 2 minus 2, oh, interesting, over 2 cubed, okay? And so what we see, 2 minus 2, that gives us 0, so everything just turns to 0, all right? So as we expected, the based on what we saw with the Desmos graph here, as we expected, the derivative ends up being 0 at this point, okay? Which means our tangent line is just going to be a horizontal line that passes through this point, okay? Now, if you guys recall, the equation of a horizontal tangent line, what we do is we just assign y equals and then just a constant value, okay? So in this case, it'll be e to the 2 over 2 squared. And so we can see that we get our tangent line. It intersects the graph at exactly one point as we want, and we know it's horizontal, okay? Yeah, and that's about it for that example. How are we doing so far, guys? Are we doing okay? Yeah, Michael, we're doing okay? Maybe. We're doing fine. Okay, pace is good. Too fast, too slow. Pace is good. Okay, cool. Yeah, feel free to interrupt. Oh. Yeah, go ahead, Samar. The log derivatives. Oh, the derivative of like a standard exponential function. We did, yes. Okay, yeah, let's get to this stuff. All right. Okay, yeah, let's chat about it, and we'll do an example. Okay, so, I guess the whole motivation behind why we care, again, we kind of summarized this whole thing on the Friday right before break, but the reason why we care about these logarithms, or more particularly ln, and why we care about ln, is the fact that when we take the derivative of a standard exponential function, the formula is this, right? So we have this interesting ln bit in here, okay? Now, ln is just a special type of logarithm, all right? So now let's quickly summarize what we know about logarithms. So the main takeaway for logarithms is that the exponential function and the logarithmic function are inverses of each other, meaning they just cancel each other out. All right, so here we can see that if we take the log of an exponential, right, so log of base b of b to the x, we just get the exponent back, okay? Or if we do the opposite, if we take the exponent of a logarithm, then again, we just get that value of x back, right? So you can kind of think about this as, I put an example here. If you take the square root of something that you just squared, you get back to the same thing, right? So if we take 4 and we square it, we get to 16. And then if we take the square root of that, we get back to where we started, we get back to 4, right? And so exponentials and logarithms work in the same way. If you do one, then the other one, you're basically just undoing what you've already done, okay? So I did some examples here, and some just quick examples. I think on the Friday right before break, I called the logarithm kind of like a exponent finding function, okay? So essentially whatever our base is, right? So in this case, we can notice that the base is 2. If I turn whatever is inside the logarithm to have that same base, the answer that this operation spits out is just whatever the exponent is, okay? So the logarithm, again, is the way that I like to think about it is certainly an exponent finding function, okay? So log base 2 of 16, I turn 16 into 2 to the power of 4, and that answer just spits out whatever the power is of my exponent, okay? Log base 5 of 25, so I change 25 into 5 squared, and I just get the exponent back. 27 is 3 to the power of 3, and I just get my exponent back, okay? Now, on Friday, right before the break, we talked about, well, we introduced e, but we also introduced this natural logarithm, okay? Now, the natural logarithm is just a specific type, or a logarithm with a very specific base, okay? So the natural logarithm is just like any other logarithm, except that it has a base of e, okay? And we kind of define that separately, and we give that a special name. We call it a natural logarithm, and we use the symbol ln for it, okay? Now, all of this was done in service to introduce what the formula was for the derivative of just your general exponential function, right? So any exponential function that doesn't have a base of e, we have to apply this formula to it, okay? Now, the way that this formula works is we keep the exponent part the same, right? So let's say we're taking the, if we're taking the derivative of, let's say, 2 to the power of x, okay? So the first part stays the same. I get 2 to the power of x there, okay? But I have to remember to tack on just a ln of 2, okay? So I have to multiply this entire thing by ln of 2 to follow along with this formula, okay? And so it's just, the formula itself, the rule itself isn't super complicated. It's just something that you have to remember to tack on at the end, okay? But this ln 2 here, the thing that you have to remember, ln of 2 is just some number, right? So in this case, ln of 2, you can punch it into your calculator. This thing is 0.69314, blah, 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 blah. Okay, so this is just a constant number that we tack on to it, that we tack on at the end. Okay. Okay. Samar, did that kind of clear up logarithms and natural logarithms a little bit? Cool. Okay, excellent. So let's do a quick example on the derivative of a general exponential function. Okay, so here's a word problem. So on January 1st, 1850, the population of Gold Rush Town was 50,000. And the size of the population is then modeled by this function. P at t is 50,000 times 0.98 to the power of t, where t is just counts the number of years since our starting date. Okay. So first thing, let's calculate what the population of Gold Rush Town was on January 1st, 1900. Okay. So let's write the function down here. So P at t equals 50,000 times 0.98 to the power of t. Okay. If we analyze the years here, we're interested in the year 1900. Okay. Now the year 1900 is 50 years after 1850, and so in this case, our t value is 50 years. All right. So I just want to figure out the population at that time. So I'm not interested in how the population is changing. I just need to know how many people are in the town at that moment in time. Okay. So what I'm going to do is I'm just going to plug in 50. So P at 50 is 50,000 times 0.98 to the power of 50. Okay, I'm going to type this in, 50,000. I get a value of 18,208 well, no points, right? So 2008 people. Okay. So it seems like the population has declined, right? And that should make sense. I mean, given the context, right? It's a gold rush town, so once all the gold is pulled away, there's nothing left. People leave. That generally is what happens. Okay. Okay, so that's interesting, but perhaps more interesting is how quickly the population is shrinking at this moment in time. Okay. Now, in order to figure out the rate that the population is changing at, what we're going to have to do is take the derivative, right? And when we compute the derivative, if it's a positive number, it means that the population is going to be increasing. But if the derivative is a negative number, it implies that the population is going to be decreasing because the slope is negative, right? So if the slope is negative, then that tells us that our population is getting smaller with time, right? So to answer part B here, at what rate was the population of Gold Rush Town changing on that date? We have to take the derivative. All right. So dp by dt is equal to. Now, if I look at this function, there's a couple parts here. So the first part, the 50,000, that'll just stay the same, right? That's a constant. I just keep it out in front. Okay. But this second part here, I'm gonna have to take a little bit of care with. All right. So for the second part, it is an exponential function, okay? Now, because it's an exponential function, I'm going to be applying this rule here, okay? So my derivative rules for exponentials, I keep the function the same, but then I have to remember to multiply by ln of whatever the base is, all right? So I'm going to keep the exponential part the same, but I have to remember to multiply by ln of the base, okay? So ln is 0.98. Okay. Alrighty, now that I've done that, what I can do is I can actually figure out what the change in the population is at this moment in time, okay, at t equals 50. So at this point, I'm interested in the derivative when t is equal to 50. So I just plug in 50 into our function here. Right. Now, all of this, I'm going to plug it in one shot into my calculator and get an answer. I get a value of negative 367.86. Okay, which I guess we can approximate as negative 368. Okay, but because this is a word problem, we want to have some sort of summarizing statement. Okay, so in this case, we say, therefore, the population of the town is decreasing. And the reason we know it's decreasing, and we'll talk a lot more about this over the next week or so, the reason we know it's decreasing is the fact that we have a negative sign out front of our slope, right? So the population of the town is decreasing by 368 people per year. Okay, and that's that. So the formula itself isn't too complex. We just have to, again, you take the derivative like you would take the derivative of e to the x. You just have to remember that you have to tack on a ln of whatever your base is. Okay? Any questions about that one? Are we pretty good? Oh, good. Excellent. Okay. Okay, so a few more examples. Now we're getting it back into derivatives of sine and cosine. Okay, so again, as we kind of, I think we did a little bit of justification. We drew some graphs of sine and cosine on the Friday, but just so we can see that again, if I plot sine of x and cosine of x, and I just kind of squeeze in here a little bit. That's not what I wanted. Zoom in a bit. Okay. So if I focus on sort of the area right around the middle here, okay? So if I look at sine of x, which is my red curve here, I can see that it is increasing at 0, and indeed I notice that the value of cosine is 1 here, so the slope of sine seems to match up with the value of cosine. If I look at what sine is doing here, right? Sine is at 0, and the slope of cosine is 0. So it seems that these two are very intricately linked as far as their derivatives go. And indeed, what we saw was that the derivative of sine is just cosine, and the derivative, oh, I made a mistake here, a little typo. The derivative of cosine is minus sine of x. Okay, so we have some nice rules for the derivatives of sine and cosine. All right. And so I know we went through a few examples on the day before break, but let's do 1 or 2 more here, just some quick ones. So determine the first derivative of cosine of 1 plus x to the power of 3. All right. For this one, we have an inside function as well as an outside function. Okay. And so that tells us that we're going to have to use chain rule. Okay, because we have an inner function and outer function. All right. So the way that chain rule works, if you guys remember, is if I have a function h at x equals f at x, or sorry, f of g of x, so I have a composition of functions, then the derivative, or h prime of x, is given by f prime. So I take the derivative of the outer function, but I keep the inner function the same. And then I just have to remember to multiply by the derivative of my inside function. Because in here, what we have to notice is that it's cosine of 1 plus x cubed. Like 1 plus x cubed is in the argument of cosine. Yeah, cool. That's actually a pretty common thing that comes up, is a lot of students see cosine something and they think, oh, it's cosine times this, right? But cosine by itself is meaningless, right? Cosine doesn't have any significance. Cosine of something has significance, right? Cosine operates on a number, or in this case, an expression, right? Okay. So yeah, not product rule, definitely chain rule. All right, so let's apply our chain rule. So I start off with the derivative. I start off with the derivative of my outer function, right? So now my outer function is the cosine function, okay? So the derivative of cosine is minus sine. So I'll get minus sine. And now the chain rule tells me that I take the derivative of the outer function, but I keep the inner function the exact same, okay? So I'm going to keep my inside function the same, 1 plus x cubed, all right? And that is the derivative of my outer function, okay? So that's fine. But I have to remember to multiply this thing now by the derivative of the inner function, okay? So now in this case, the inner function is just that little polynomial bit there. So derivative of 1 plus x to the power of 3 is just 3x to the power of 2, all right? And then I'm done. That's it. I've taken my derivative. All right. Any questions about that one? Are we good? Okay. One more example here. Now we're going to kind of mix and match. Here we have the derivative of an exponential function, but the exponent, or the power in this exponential function is itself a trig function, okay? So again, we have a outer function. So in this case, our outer function is e to the power of something, okay? The inner function is sine of x plus cos of x, all right? So again, we are going to have to apply chain rule here. No, it's close to 1. So the only one that we have, so we can apply this one, but we have sine squared x plus cos squared x equals 1. But not sine x plus cos x. That doesn't help us anyway. Yeah. Yeah. Okay, so can't apply trig, although that's a good point. Like you should, especially when you're dealing with trig functions and derivatives of trig functions, you absolutely 100% should always try to apply a trig identity if you can to simplify it, then take the derivative, right? We saw a bit of that in chapter 2, right? I think I had a question on your guys' quiz. I think I asked you to explain. Yeah, it was the question that I had on the quiz for you guys was, if you remember, 1 over x squared plus, or sorry, 1 over 2x squared plus 3 to the power of 3. And I asked you 2 different ways to kind of explain how to take the derivative of this, right? So one way is you just go forth and use the quotient rule like you normally would. The other way is to first flip this, 2x squared plus 3 to the power of negative 3, and then apply the power rule and the chain rule. And that way, both of you recognize that way is way easier to do in the end, right? It's just quicker to get there. So similarly, if you do have some sort of trig identity that you can apply first, do that because it will make it a lot easier. All right. Okay, back to the example. Let us take the derivative. So y prime. So again, I'm applying the chain rule here. I start with my outer function, right? So in this case, e to the x. Well, that's fantastic because the derivative of e to the power of something is that same thing, right? So e to the sine of x plus cos of x. So nothing changes there. That's nice. Okay. But here comes the chain rule part, right? I still have to remember to multiply by the derivative of my inner function, all right? So the derivative of sine x plus cos x, that is cos x minus sine x. Okay? So that's the derivative of my inner piece there. All right? And that's it, right? We can't really do much more here. We can't mix and match these things. They're sort of isolated, right? We could expand out the bracket, but that just gets that's almost undoing what we want, right? That's getting less simplified, not more simplified. All right. So at this point, we're done. Don't have to do anything else. Okay, cool with that one. Quick little example, nothing too tricky. Okay. Now, last but not least, I only have one more example here, and then we'll have a little chat. So I know that in on that last day there, we actually derived the formula for the derivative of tan. Okay, so I left out these steps in these notes. I think you guys already have them. If you don't, you can retry it, right? So we have sine and cosine, and they're being divided by each other. So you apply your quotient rule there. So if you guys don't already have it in your notes, you can kind of rederive it. The main takeaway with this example here is that all of the rules that we've learned still certainly apply to this, right? So if we want to take the derivative of sine of x plus tan of x to the power of 4, we're going to have to use chain rule, right? Because again, we have an inner function, right? Our inner function in this example is sine of x plus tan of x. And then with that, we have an outer function, right? This x to the power of 4, or this something to the power of 4 is our outermost function, all right? So we're definitely in a chain rule scenario here, all right? So let's take the derivative. So dy by dx equals. So I start off with the derivative of the outer function while keeping the inner function the same, all right? So I pull down the power of 4. I have sine of x plus tan of x. That stays the same. And I decrease the power by 1. That is the derivative of my outermost function there, all right? But because it's chain rule, now I have to remember to multiply by the derivative of the inner function, all right? So the derivative of the inside function, I have sine of x, so derivative of that gives me cosine of x. Plus, now I have tan of x. Now, up here, we have the formula for the derivative of tan, right? Derivative of tan is secant squared of x, okay? So I'm going to use that here. So I get cos of x plus secant squared of x. Okay. And then I'm pretty much done, right? I can't really mix and match these. You could try to apply a trig identity, but there really isn't any, right? So from here, we're pretty much done, right? That's as simplified as we can make it, right? We have successfully taken the derivative of our inner function there. Okay. Okay, so that's about it from me. That's all I've got. I do want to have a quick chat, so I'm actually going to stop this and switch